Hi guys. My talk is on quantum computing and how it differs from the classical computers that you use every day, right? Your mobile phones, your laptops. I'm sort of the agenda is to sort of get you a little familiar with classical computers and then introduce you to the concept, the building blocks of quantum computers, qubits, and then just touch upon something called Grover's algorithm. It's a quantum algorithm and how it works. It won't be very heavy. Firstly, because there's not enough time to cover it, and secondly, because I don't have enough knowledge on the same. So I'll keep it accessible. Uh, so let's get started with, and you can stop me anytime to if you have any questions or doubts. So the first, we'll start with classical computing. You have your everyday computers, laptops, and mobile phones, and the simplest unit is a bit. A classical bit. I'll come to. So you have an on and an off. Think of it like a light bulb. You have zeros and ones, on and off. Uh, Using zeros and ones, you represent everything: text, images, songs, videos, basically everything. At the heart of it, you have numbers, and you represent everything on your system using numbers. So so let's get to it. You have four boxes. Okay, you have four bulbs or boxes. You have four human beings. Anything. So it has a state on and an off. Okay. So this is an on state. This is an off state. On. I mean, sorry, off and on. And using that, you represent numbers. So think of think of this number 768. So what does 768 mean? You have the hundreds place over here. 7 times 100, 6 times 10, 8 times 1. That gives you 768. The decimal system. You have 10 possible states in every box, and you get a number. But in computers, it's called a binary system. You have two possible states for every box. So say I have this number 100. Uh, so the first place is the ones place. The second place, since you have two possible states, it multiplies by a factor of 2. In the example of 768, you have the ones place, the tens place, the hundreds place. Because you have 10 possibilities, 1 to 9 and a 0, it sort of expands by 10. It grows by 10 times. So the number 100 is actually 4. 1 times 0, sorry, 0 times 1, 0 times 2, and 1 times 4. With me here? With me so far? So what is this? What is this? 1111. 1 plus 2 3 plus 4 7, 15. So it is 15. So as you can see, with the binary system, you can represent. You need larger number of bits to represent numbers compared to the decimal system. And decimal system, it's come across because we have 10 fingers. So that's why humans invented the decimal system, because it's sort of natural for us to count using our fingers and then expand on that. With me so far. So you have binary system where computers represent everything using two possible states, and you have a series of boxes which represents images, blah blah blah. So now we've represented numbers. Coming to text. So by the same concept, this is 112, this is 115, this is 105, this is PSI. So the world has come together and they've decided, okay, these particular numbers, it means this particular alphabet. So it's called the ASCII code, and so 112 is P, 115 is S, and 105 is I. So it represents PSI. So you can represent text in computers, right?
Sorry, what does PSI stand for?
Pine size and size.
Oh,
You're concentrating a lot. I like it. Yeah. And then you have images and videos, right? So you again numbers. So you have something called RGB triplets. You tell it how much red you want, how much green you want, how much blue you want. So pure red, it means you want a lot of red, 250, 256, and nothing of green and blue. I mean yellow, right? The primary colors, yeah. So, so this is how classical computers work. They have, like they've evolved over time. I can represent the classical computers using human beings just with light bulbs, and with modern computers, you have RAM and you have such small capacitors. You can fit billions of them on a 3 inch by 5 2 inch strips. So now coming to qubits. And one thing to note here is these are all concrete values. The computer is in a particular state. So now you have bulbs here. This one is turned off. These two are turned on, and you have a fixed state. It's not probabilistic. I'm standing right here, right? It's a sorry, yeah, deterministic state right now. Yeah. So now coming to a qubit. So a qubit is sort of a probabilistic distribution, a probability distribution. Say, for example, you were assuming yesterday what is the state whether I'll be here or not. I might come here today. I might have not turned up today based on circumstances. So it's both. There is a possibility that I'll come here. There's a possibility that I will not come here. Say it's a 50-50 possible. It's a 50-50 probability distribution, and so you have 4 bits here. So how many possible states? Like what are the possible states? So I have 3 digits. I have 999 possible states, right? So it is 10 to the power 3, 1,000 possible states. So in binary systems, I have 4 possible boxes, 4 possible places. So the number of possibilities is 16, 2 to the power 4. Like this is 15, right? So starting from 0 to 16, so 2 to the power 4. I have 16 possible outcomes. I can represent 16 possible outcomes using 4 bits. Uh, so a qubit is sort of a representation of all the possibilities. One qubit can represent 2 states, either on or off. It's not fixed yet. It has a certain probability. So 4 qubits can represent 16 possible outcomes. It is not telling you, okay, it is this. This particular bit has a 50% probability of being 0 and a 50% probability of being 1. The second thing has a 90% probability of being 1 and a 10% probability of being 0. It's probabilities. Like it's you would have heard of quantum superposition, right? Like it being both the things at the same time. This is basically it. It's probability. So now, how do you represent a qubit uh, in a physical system? Like on and off switch in a strip of RAM, you have high voltage, which is 1, and low voltage, which is 0. So the same thing, the possibilities. How do you represent this in a physical system? Let's have a look at that. So there are multiple possibilities. The one which I understood was an oscillator. So you have something which is changing from 0 and 1, which is frequently, it is fluctuating between 0 and 1. If you look at this, it's almost an equal split. It's changing from 0 to 1, again back to 0, back to 1. It's almost a 50-50 split. And in this case, it's a 30-70 split. It's 70% of the time it's 1, and 30% of the time it's 0. So so if I were to make a quantum computer, a qubit, uh, if I were to represent probabilities, each qubit would sort of flip. It would flip its state. With me so far, it's not constant. It's changing. And when I measure the voltage, it would probably give me 0 or 1. Okay. So So now one important aspect here is, so when it comes to classical computers, you can manipulate individual bits, but in quantum computers, you have to think of the entire system. I have 4 qubits, so I have how many possibilities? 16 different possibilities. Uh, so you won't think in terms of individual bits, and once you take measurement is as in, so now you're assuming, okay, will Abhirath come for the talk or not? You don't know it as of yesterday. So you come today and you have a look, okay, Abhirath is here. That is sort of measurement. Measurement can also be in terms of, you have something to measure voltage, and you actually measure the voltage. So is what is the voltage of this particular capacitor? Is it holding charge or is not holding charge? So that sort of thing. So now we'll take an example of a search algorithm in classical computers and uh, in quantum computers. We won't go deep into the exact working of. I'll give you a sort of, okay. That's you'll get to know. So you have, say, 1,000 items, and you want to search for a particular item in a classical computer. So you'd obviously have to. It's unsorted. You'd obviously have to look at it one by one, right? So you have 1,000 items. So what is the worst case? You find it at the towards the end of it, right? So, uh, so the worst case scenario is 1,000. You have to go through 1,000 operations. You're looking through each one of them one by one. So as the problem grows in space, the problem grows in size. The number of operations performed by a classical computer. Think of a large strip of RAM. You're going through the bits one by one. Like you have 4 bits here. You're going through it. This is not what you're looking for. You're going to the next 4 bits. Okay, this is not what I'm looking for, and so on and so forth. You have to go through. You have to go through search 1,000 such items. So what Grover's algorithm does is, it's sort of, instead of 1,000 or instead of 10,000 items that you have to search, you won't have to search for all of them. So the way it sort of works is, uh, so it creates an equal probability distribution. So you have 10 qubits, so that is around 1,000 items. It says, okay, each of them it has an equal probability of 1 by 1,000. Okay, so equal probability distribution. It sort of pushes it sort of works in a way. So it has something called an oracle function, which I don't understand it yet, and there's no time to explain it also what I understand. So it sort of pushes the right probability. It sort of nudges. So now you have 4 possible states here, right? You have 4 possible states. Now each are at a distribution of 25, 25, 25, 25%. So when I take measurement, I might get the wrong answer. There's a possibility I might get the wrong answer because everything has a probability distribution of 25%. So the way Grover's algorithm works is, it uses something called the oracle. In physical representation, it uses a laser to manipulate the oscillator. We saw an oscillator right here. It uses small lasers to manipulate the oscillator. If, say, it started out with 50-50 split, it would make it a 70-30 split. It would slowly nudge it towards a 90-10 split, a 99-1 split, to change the probability distribution, to nudge it towards the right answer, and it would keep doing that a certain number of times. The theory says, it instead of searching it 1,000 times, like when you use the classical computer, you have to go through 1,000 items. You just have to do it square root of n times. There's a big mathematical proof for it, and it would suppose C is the right answer. It would change the probability of this, all the oscillators in the physical realm that we are in. It would change it to it would make it almost 100%. And when you measure the outcome, you get the right answer. So that is the sort of the crux of quantum computers, where you have qubits which have a certain probability. which is also called quantum superposition in lot of you've heard of quantum superposition, right? Like a lot of you would have heard it. And yeah, that's pretty much it. And where the speed up comes from, why is it faster? A lot of theory, there are a lot of theories. So two of the most popular theories are you have parallel universes where that's where the speed up comes from. Another theory is you have a branch where you you sort of take a particular decision and you sort of dive into that branch of. So I don't understand it exactly, but yeah. So this is, yeah, that's pretty much it. Yeah. Yeah.
I was fully lost.
Okay.
But so can you tell me, these are three concepts, right? You have qubits, then you have
Uh,
quantum computers, and how they function, and then the rovers.
right.
So of these three, what is the thread I didn't fully understand?
Huh.
And second, can you explain it to me like a 12 years old?
Okay.
Because I can't.
So the first part was classical computers. How using just voltage, how using current. So current is it's either there or it's not there, right? So it's just two values, and we have multimedia, which is like you have colors, you have millions of colors, you have text. So the first part was how classical computers work, and how just two values can represent infinite values. That is classical. That is the classical computers.
Yes.
So that was clear, right? The numerical system 1, 2, 4, 8.
Yes.
So quantum computers is, so what operations we perform on classical computers? We don't perform on probabilities. We perform on distinct values, zeros and ones. We perform it one by one. But when it comes to qubit, it's simultaneously both. It is a probability, right? So the theoretical concept is, uh, instead of doing everything one by one, like for example, you have two bits here, right? You have four possible states. A classical computer would have to go through all possible states one by one. But a quantum computer, since these four states are represented by two bits, you have some matrix operations. You would cover all these four states all at once. Instead of uh, instead of going through all of them one by one, you would have a certain operation that would cover all these four states in this at once, all at once.
I think what would be really simple is if you take like the exact same addition problem or the multiplication problem
Right.
and explain it how numbers are represented on qubit versus like, I think that would just ground all of these
Right.
because Grover's algorithm is particularly difficult to intuitively grasp.
So addition using quantum, I don't think it works that well. You have very specific algorithms which work on quantum computers.
Like RSA,
Yeah.
stuff like that. Right? So I think if you distill those problems out into something that's easier to break down, like you make it into something like 1 1 1 1 0, and then you see how this computer would do it versus that. You clearly see like, okay.
I think what I understood is that the computers basically breaking whatever the algorithms are, is breaking everything down into buckets that are making the selection and distribution. And how those buckets are broken down is a sense of probability distribution. So depending on the kind of distributions that have come up, I don't know, frequently or whatever, any math that the formula is using, it's breaking it into buckets, so it's faster to actually find and compute whatever you're trying to do. So essentially putting it into groups of some kind. That's essentially what's happening.
Yeah, in a way. So it's sort of doing it all at once. It's like you would have to go through it like two bits. You have four possible states. You're going it one by one, but a quantum computer goes through it all at once.
All at once.
Yeah. So that is the overarching idea. But the example, like even only two algorithms, like Grover and Shor. So
You were struggling to reuse the parallel universe example.
yeah.
It's very hard to explain. I don't understand, but
Yeah.
No, but it was so interesting to see how passionate you are, and I can see how intelligent you are.
No, I don't understand this. I don't understand this.
I'm
Yeah.
curious about like the story that made you interested in this.
So I just wanted to understand what's the big deal about quantum computers, and like as programmers we study algorithms, right? So there was a breakthrough that okay, it's able to factorize things very fast. So that is what got me like, yeah.
That's
Okay. I think that's pretty much it. So break it down to a simple example.
So there is something else in between,
Huh.
which is what this company called Extrop is doing.
Extra.
Extrop.
Okay.
What they're saying is between having these quantum and classical, there's something in between
Okay.
where you model probability distributions using different types of values. So, like for example, right now we're using silicon inside this bucket to go between 0 and 1. So what if you use something like aluminium oxide? Right? So there you essentially have a very specific probability distribution with which you can represent this 11101. Right now you can essentially do interesting types of mathematical problems. So what, particularly in the machine learning space, because you're essentially approximating probabilities, right? So what if you essentially change the substrate from 1 to 0 to like a more fluid medium, and then you do math on top of it. It's like more information. There's no bits anymore. It's like this. Yeah, it's like there are certain sets of functions. Like for example, if you touch it, if you measure it now, it'll be 1. If you measure it another time, it will be 0, 1. So it's essentially changing at that level.
So it's then
Yes.
What was the def?
There's another company called Normal Computing based out of New York. So those guys have already run some more interesting models on it. That is a lot more accessible to explain.
Okay.
And especially because you can use simple machine learning algorithms, and you can clearly see why one is better than the other. Like
Okay.
literally.
What is the name? Can you repeat the name again?
It's I don't know. I think it's thermodynamic. Yeah.
Okay.
But I heard that there's a bunch of getting from that website. I'm not sure about normal computation.
Normal computing is another company. Yeah. So these guys are not as popular on Twitter as the other guys. They're actual researchers. Like they don't care about bringing it up. These guys are very Twitter mimetic.
But I never understood where the speed up is coming from. Like all the explanations, you have a matrix multiplication. It's still going through n operations, right?
It's not going to an operations. That's still annoying because you're essentially stacking these multiplications into like some sort of superimposition, like at a physical level.
Yeah, but the oracle, it goes through all the n items.
Right.
So the oracle says yes or no to the n items. Yeah, quantum science. Okay.
I found this more accessible.
Okay. So I still don't understand. Like in theory, I'm able to understand and parrot it back. I'm just parroting back what I read, but I still don't understand where the speed up is coming from.
No, but I don't think matrix multiplication can be optimized by quantum algorithms.
That's not the point. Yeah, I don't think so. Yeah. Not yet.
It's not optimizing matrix multiplication. The theory says it's just one tensor operation, matrix multiplication, and you get all the possible answers. But even then, you go through n items, right? So that is what I'm not able to.
Yeah, I mean, I don't think we should look at quantum as a replacement for classical computing.
Right.
Yeah,
There are certain algorithms which will
Right.
benefit from.
because classical is not deterministic. It's built on a very factual thing or one what you're saying about quantum computing is that there are probabilities. This is more likely than the other, and so it's probably picking up speed. But this is bunching together more likely. It's not the same, like you said. It's just to speed up things and to make things that could sort of be 80%, 90% more probabilistic than
Yeah.
Okay then. Thank you guys. Any
Thank you.